Now, just picking up where we have left off, okay, and we have for equations of various types, we've had like categories like conditional, contradiction, as well as identity, and also we have looked into quadratic equations, solving in all different kinds of capacities, and we will re-enter that particular phase once again with what we have looked into most recently and will continue. And this is where we have equations that consist of rational expressions. And we have from page 69. Okay, so we have an equation where we have 1/3 minus 4 over 3t is equal to 7 over t. And now, when we looked at combining rational expressions, okay, we had written everything in terms of the least common denominator, where we would have had all the fractions in terms of the least common denominator. Now, since we're looking at solving equations, we're going to use the least common denominator, not in terms of writing all the equations with the least common denominator as the denominator for all fractions, but we're going to use it to get rid of the denominators and be able to express what we have in the variable in direct terms. So first of all, so we have 1/3 minus 4 over 3t is equal to 7 over t. And we have with the restriction from the get-go, okay, whatever we have for t, we cannot have a zero denominator. Okay, so 3 is already non-zero. 3t cannot be 0, so t cannot be 0. And we have ditto for just t itself. So we have a restriction that t cannot be equal to 0. And for what we have in the case of the least common denominator, and the smallest term that all of 3 and t will go into will be 3 times t. And so picking up with the least common denominator and multiplying all the terms in the equation by 3t. Okay, so you have 3t multiplying 1/3. And then we have subtraction, and we have 3t times 4 all over 3t. And we have is equal to 3t times 7 over t. Okay, and just looking at what we have now, okay, you can sort of cross multiply and just go ahead and get to the next phase, or you could just do the gradual reduction. Okay, you have like 3t times 1/3, you have like 3t over 3. And we have minus 3t times 4. So you have 12t over 3t. Again, you can cross multiply as another option. And we have 3t times 7. So this will be 21t. And we have all over t. Okay. And just for the reduction, now like you have 3 will go into 3t, t times 1 still goes to t. You have minus, and again, 3t's would go out, and you have 4 left over. And that should have been 12t over 3t. Okay, so you have minus 4. And we have 21t over t. So this will go to 21. And for our apparent solution, okay, so we have t minus 4 is equal to 21. And so we have that t is equal to 25. Okay. And the stipulation or the restriction that we have for t is that it cannot be equal to 0, and 25 satisfies that particular restriction. Okay, so there's one solution in t, and that is going to be at 25. So this is a case of a conditional, where this equation is true on the condition that t is equal to 25. All right. Now, in the case of what we have with number 74, and we have for this particular problem, okay, now we're going from the variable t to the variable c, okay, and we have for this one, okay, so you have so we're looking at solving for c, And we have, just like what we had in the terms in the variable t, we got terms in the variable c displayed solely in the denominator position. Okay, so right now we have 2 over c plus 3 minus 1 all over c minus 3. And we have is equal to 10 over c squared minus 9. And we have, for the last denominator, we have a difference of squares that will factor out to the previous two denominator expressions. Okay, so we have in this one, okay, so we have I'm just going to try to copy this. There we go. Okay, so for the difference of squares in the last denominator, again, this will factor to c plus 3 quantity times the quantity of c minus 3. And now we have for c, okay, there will be some restrictions. Okay, so you have that c plus 3 cannot be 0. And we have that c minus 3 cannot be equal to 0 either. And so we have that c cannot be negative 3 or positive 3. Okay, so those are going to be our restricted values, negative and positive 3. And for the least common denominator, again, that's going to be c squared minus 9, or in its factored form, we have the quantity of c plus 3 times that of c minus 3. Okay, and so we have just taking the least common denominator, and again, just canceling out the denominators. And again, you're going to do cancellation with the least common denominator if you have equations involved. So just taking what we have here. Okay, so we're distributing the least common denominator, okay, over the terms. And again, if you see the distributions in advance, that's fine. I'm just sort of giving you a bit of an expository layout. Okay, and just for the setup that we have here. Okay, so for the first ratio, okay, we have c plus 3 to completely cancel. For the next, okay, c minus 3 is going to go out. And then we'll have, for the last ratio, we're going to have everything in the least common denominator to cancel out. So for what we have at this stage, okay, so c plus 3's went out from the first portion. Now we have interaction between 2 and the quantity of c minus 3. And then we have bringing down the subtraction. So you have c plus 3 times 1, so you're going to have minus the quantity of c plus 3. So this subtraction is going to affect not just the c, but also the 3. And for what we have over to the right, okay, that is equal to 10. All right. And so for what we have in this particular configuration, okay, we have the terms in c now expressed in direct fashion. Okay, so looking at the distribution, so you have 2 over the quantity of c minus 3. So this will be 2c minus 6. And then we have minus c. And then the distribution of subtraction over 3 becomes minus 3. And we have is equal to 10. And just combining like terms, so we have 2c minus c becomes c. Negative 6 and negative 3 will be a negative 9. So we have that c minus 9 is equal to 10. And if I add 9 to both ends, we have c is equal to 19. And 19 is not equal to what is disallowed with negative 3 or positive 3. So 19 would check out. Okay, so this equation is going to be true on the condition that C is equal to 19. All right. Now, for what we have in the case of the next sets of items, okay, and we have a bit more detail is going to be involved, or more steps. Detail is in more steps. And for what we have in the case of number 80, okay, so we're still looking at solving for C. Okay. So right now we've got 4C all over C minus 5 for the first term, and we have minus 1 over C plus 1, and we have is equal to 3C squared plus 3. Okay. And we have all over the quantity of C minus 5 times that of C plus 1. Okay. So we have in the setup, okay, so we have for the restrictions that we have placed upon C, we have that C minus 5 cannot be 0. So C cannot be equal to 5. And for C plus 1 cannot be equal to 0, so we have that C cannot be equal to negative 1. As for the least common denominator, okay, so that's just going to be the product of C minus 5 and C plus 1. Okay, so again, we're going to cancel out the denominators. So we have upon distributing, so you have with the first term, okay, you have 4C over C minus 5. Okay, so in this one now, you would have C minus 5 to cancel out, but you would still have the activity between the entities that remain, namely 4C and C plus 1. Now we have, bring down the subtraction, okay, and we have with the next term, and still multiplying by the least common denominator. And over here, okay, so we have C plus 1 will cancel. And for what we had in the last ratio, just like the term on the right hand side of the prior equation, okay, you're just going to have a complete cancellation of the least common denominator. Okay, so looking at what we have 4C and C plus 1, so we're going to have distribution to occur. So 4C times quantity of C plus 1, and we have minus, and again, just like what we had with C plus 3 in the second term, after the clearing of fractions, have a bit of history to repeat where you have the distribution of subtraction over a binomial. And we have to the right, so you have 3C squared plus 3. And looking at what we have in the distributions, we have 4C over the quantity of C plus 1. So this would be 4C squared plus 4C, and then distributing subtraction over the difference binomial C minus 5. So we have a minus C. Subtraction over negative 5 becomes a plus 5. And we have is equal to 3C squared plus 3. And as we gather like terms in the middle of the left hand side, so you have 4C squared. 4C minus C becomes 3C. We have plus 5. And we have is equal to 3c squared plus 3. Okay, now we have a quadratic equation in the variable c, and if I display this in standard form, that is, I have the terms in descending degree order and set equal to 0. And what I can do here between the c squared terms, the lesser of the two is 3c squared. So I'm going to take this out, and I can just move the 3 by subtracting. So for what we're going to have here, okay, we have 4c squared minus 3c squared, so we have c squared, and we're going to have plus 3c plus 2 is equal to 0. And in terms of what we have with the factoring, so we have the quantity c plus 2 times that of c plus 1 is equal to 0. And entering the phase of the zero product property, so we have, upon setting each of the factors resulting from the quadratic each equal to 0, we have an apparent set of solutions with c equal to -2 and c equal to -1. And just looking at what we have in the setup, okay, so we have for c at -2, okay, okay, c is at -2, okay, so we have that's not equal to 5, and that value of -2 is also not equal to -1. So everything we have in the stipulations is satisfied with -2. However, with -1, okay, we have, again, the stipulations for c will be that c cannot be 5 and that c cannot be -1. And if you notice, okay, we have violation. Okay, so there could have been up to 2 solutions, but because we have -1 to be one of the restricted values, okay, we have only one value that will work throughout for this equation, and that is going to be c is equal to -2. Okay, all right. Now, in the case of what we have with the next item, and we have for number 81, and I will tell you, we're looking at going back to solving for the variable m, and this one is going to be very analytical. I mean, very analytical. And I thought that I would throw this one in case that there's a problem like this that will somehow show up in Alex, and just taking what we have for this problem. Okay, and this is multi-layered in terms of the approaches. So if you found this one to be a very difficult problem, don't feel bad. This one is of a bit of a different caliber in comparison to other problems in this section. And here we have m over 2m plus 1. We have followed by the addition of 1 is equal to 2 all over m minus 3. And so just taking what we have here, okay, now we have for the restricted values in m, we have that 2m plus 1 cannot be equal to 0. Okay, in this case, so 2m cannot be equal to -1, and we have for m itself, okay, we have restricted, or the restriction, yeah, that m cannot be equal to -1/2, and as for m minus 3, that cannot be equal to 0. So we had that m cannot be equal to 3, And in terms of what we have for the least common denominator, okay, so that is going to be 2m plus 1 times m minus 3. And so just taking what we have here, again, just clearing out the fractions. So we have with the first term, okay, so we have for m over 2m plus 1. Okay, and if we go ahead and interact, so you're going to have 2m plus 1 to cancel out, but we're still going to have work left over with the distribution of m all over m minus 3. And we have, you got plus 1 multiplied by the LCD, and looking at what we have for the last ratio. Okay, so we have again the quantity of 2m plus 1 times that of m minus 3. We have times 2 all over m minus 3. And in this setup we have m minus 3 to cancel out. And so for, we're going to have in the layout, okay, so from the first term, after applying the multiplication by the least common denominator, we still have left m and m minus 3 to be multiplying each other. And for what we have in the next case, we're looking at the product of the expressions or the factors in the least common denominator. So we have this one with the FOIL, we have 2m squared. Outside product we have negative 6m plus m minus 3. And for what we have to the right, so we have 2 and the quantity of 2m plus 1. And carrying out, okay, so we have m over m minus 3. So we have m squared minus 3m. We have plus 2m squared. And negative 6m plus m, so we have minus 5m. We have minus 3, and we have with the distributing on the right hand side, 2 over the quantity of 2m plus 1. This is going to be 4m plus 2. Okay, and just combining the like terms on the left. So we have m squared plus 2m squared. We have 3m squared. Negative 3m minus 5m is negative 8m. Again, we have minus 3. And we have is equal to 4m plus 2. Okay, so you have a quadratic equation in the variable m. And just looking at converting what we have in standard form. So you have the only second degree term to be 3m squared. And so just moving what we have on the right hand side of the equation. So take away 4m. Also take away 2. So we're going to have here, you have 3m squared minus 12m, and we have minus 5 is equal to 0. Now this particular trinomial is not going to be factorable. And you could think of trying to factor by grouping. And so if you took like 3 times negative 5, 3 times negative 5 is negative 15. And if you're to think of combinations that numbers that will go into negative 15 and simultaneously add up to negative 12, they will not exist in the integers. You could think of like negative 15 and 1. Negative 15 times 1 is negative 15. However, negative 15 plus 1 will be negative 14. And if I have like negative 5 and 3, well, negative 5 times 3 does equal negative 15, but in terms of adding, negative 5 plus 3 is negative 2 as opposed to negative 12. And all the other integer combinations will be positive integer sums. So in terms of a recourse, okay, we can take what we have in M and set up the quadratic formula. So we have for A, okay, A is equal to 3. And we have B is equal to negative 12. Since we have the subtraction of 12M, or whatever the first order variable term is, and we have for the constant in the trinomial, okay, we have for C, okay, that is going to be negative 5. So for what we have in the case of the quadratic, okay, now we're not solving for x but m, but we're still going on the same premises in terms of how to work with the coefficients of the trinomial. So we have negative b plus or minus, okay, the square root b squared minus 4ac all over 2a. And for what we have at the substitution stage, so negative b, we have opposite sign of negative 12. And we have plus or minus, okay, the square root, so b squared. Okay, so we have negative 12 squared. And minus 4 times 3 times negative 5. We have all over 2a, which would be 2 times 6. Okay. Now I'm just going to mention for what I have inside the radical. Okay. Now negative 12 squared. Negative 12 times itself is going to be positive 144. Now for negative 4 times 3 times negative 5. Negative 4 times 3 is negative 12. And then we have in turn negative 12 times negative 5 is going to be a plus 60. Okay, and so we'll have 204. And while 204 is not a perfect square, it is nonetheless a kind of even number where the square root of the amount is reducible in square root terms. So for what we have now, we got opposite sign of negative 12 is a positive 12, and we have plus or minus, and we have the square root of 204, and we have all over 2 times 3. My bad. Guess I was doing a little bit of multiplication in advance. I have 2 times 8, so I have 2 times 3, so that is going to be at 6. Okay, so we have with the square root of 204, okay, now for 204, now again 204 is a rather large number. Now the highest perfect square divisible into it is only going to be 4. So I have the square root of 4 times 51, and just separating. So I have the square root of 4 times the square root of 51, so this will be 2 times the square root of 51. Okay, now, so just taking what we have at this stage. Okay, so we have 12 plus or minus. Okay, we have 2 times the square root of 51. All over 6. And just taking what we have now, okay, so 12 plus or minus 2 times the square root of 51 all over 6. Now if you notice, we have even valued leading coefficients, and there are sort of 2 pathways you can go regarding this. Now we can factor like 2 halves from this ratio. In other words, like with the denominator, 6 is going to be 2 times 3. And for what we have in the numerator, if I factor out the 2 will go into 12 6 times. And 2 will go into plus or minus 2 times the square root of 51. So you have the square root of 51. And here we're going to have 2's to cancel. And so we have 6 plus or minus, okay, the square root of 51 all over 3. And I will just kind of mention this as well. If I were to break apart what I have here, so 12 over 6 plus or minus 2 times the square root of 51 over 6. 12 over 6 becomes 2. Yeah, plus or minus. Now for 2 times the square root of 51 over 6, now the 2/6 part reduces to 1/3. And so this will go to the square root of 51 all over 3. Okay, and if you notice, we have, for the first version, you have the compact answer. Okay, where we have everything put together or compressed together as a single ratio, where we have all the 6 plus or minus the square root of 51 over 3. But if I detach the 6/3 parts, or what results as the 6/3 part, from the rest, and we have 2 by itself, and then we have plus or minus, again, the square root of 51 all over 3. So those are 2 ways that you can express, okay, the simplified result. But I think it would take both, and let me mention this. I think I bring it up in the simulation video. Well, I know I do, but in Alex, okay, so if you took this answer, what you would want to do is put the answers in terms of like 6 plus the square root of 51 over 3, and 6 minus the square root of 51 over 3. But if you had it like separately, okay, you have like 2 plus the square root of 51 over 3, and 2 minus the square root of 51 over 3. So you have 2 plus the square root of 51 over 3, 2 minus the square root of 51 over 3. And Alex, if you do not have the parentheses, but if you want to express what we have here, and I've seen this plenty of times where, one in a sense got the answers correct, but because the parentheses were not in the syntax, so to speak, it's like Alex could not automatically read it. Okay, so if you're looking at the compact ratios, do not forget to include the parentheses. All right, and now, yeah, so 81, very analytical, to say the least. But now for what we have in the case of 82, this one is somewhat analytical, but not as, I guess you can say, for lack of a better term, not as excruciating. But for 82, now we're looking at solving for z. And in this one we have 7 plus 20 divided by z, okay, is equal to 3 over z squared. Okay. Now for both z and z squared, okay, these cannot be equal to 0. So there is one restriction that we have for z, and that is that z cannot be equal to 0. Now for what we have in the case of the least common denominator, okay, you have the smallest term that both the z and z squared will go into. Okay, that's going to be z to the second. And if I multiply all the terms out by z squared, I'll just arrange this where z squared will follow each term, so you have 7 times z squared. You have 20 over z times z squared. You have 3 over z squared times z squared. I'll just copy this part. I'm going to put this in reduced terms. Okay, so we have 7z squared. Now for z into z squared, okay, now you're going to have the complete cancellation of z, but you're going to have a degree in z left over. And for 3 over z squared, okay, z squared completely cancels out. So looking at what we have in distributing, so we have 7z squared plus 20z, okay, is equal to 3. And if I display what I have here, in the general quadratic form, or the standard quadratic form, okay, so I have 7z squared plus 20z minus 3 is equal to 0. And now for the factors, now you got 7z squared will go to 7z and z. Okay, now I mentioned just kind of step to the side here. It's like, how do I know that 7z squared can go to 7z and z, and in terms of how to follow through? Okay, now again we have with 7z squared plus 20z minus 3. Now if I were to kind of do the factoring by grouping, so I've got 7z squared. Now think about it like this. 7 times negative 3 is a negative 21. And what factors negative 21 will add up to 20? Well, in this particular case, you would have negative 1 on the minus side and plus 21 on the other. So you would split up the 20z into z terms. So you have like negative z plus 21z minus 3. Again, the coefficients, negative 1 times 21 has a product of negative 1. And again, the sum of negative 1 and 21 comes out to the middle coefficient, 20. And just taking what we would have here, so you have 7z squared minus z. And we have plus the quantity. We have 21z minus 3. And so for 7z squared minus z, highest order term is going to be z. So z times quantity is 7z minus 1. And we have plus, and for 21z minus 3, okay, the greatest common factor is going to be at 3. And this will go into the last set of terms, 7z minus 1 times. So the factorization will be that which is shared, in this case 7z minus 1, and coupled with that, okay, you have the combination of the outside terms and operation. Outside terms being the greatest common factors from the pairings. Okay, so we have for the what we have in this problem. So we have the factorization. We have 7z minus 1 and z plus 3. And so for what we have in setting each of the factors to 0. Okay, so we have 7z minus 1 is equal to 0. Adding 1 to both sides. And we have with division. So we have that z is equal to 1/7. As for z plus 3 is equal to 0, we have another apparent solution with negative 3. So for what we have in the overall picture, okay, now again, whatever we have for z cannot be equal to 0, and instead of 0 we have a positive and a negative value. So the stipulation is satisfied with both of these amounts for z. So we have this equation, okay, has two solutions with positive 1/7 and negative 3. Okay. All right. So you've had equations involving rational expressions where the clearing of the fractions has led to either a linear equation, and just like the last few problems, also potentially quadratic equations to work out. And that number 81, okay, that was a pretty nasty one. A lot of steps involved and clearing out. And again, just for our solutions here, yeah, I think the stipulation that m could not be negative 1/2 or 3 definitely satisfied. Now, in crossing over to what we have in the next item, and this is it's going to sort of tie in some of our earlier concepts working with the square root property of equality aspect of quadratic equations. And here we're going to have radical equations. And in the case of radical equations, there is a principle, or property rather, and this is what's referred to as the principal square root rule. And this states, okay, this is going to be for like the principal square root rule, and this is going to apply to even index valued roots. And this rule states that the square root or any even root for that matter. Okay, what I mean by this, okay, so you have like the square roots or any even root, and like the square root, fourth root, sixth root, and so on. Okay, now with square roots, okay, again, square root, it's implicit that the index number is going to be 2, but you don't normally see that index number. And the square root or any even root of an expression cannot reduce to a negative constant. Okay, and let me kind of give you a little bit of a segue here. When we had dealt with not the principal square root rule, but the square root property of equality. Okay, we have like x squared is equal to 36. Okay, that means there is potentially up to 2 solutions if the equation is a conditional, which this one is. So we have up to 2 solutions possibly, or possibly up to 2 solutions. And with the square root property of equality, again, when we went from x squared to x, we had plus or minus the square root of 36. And again, we had the x was plus or minus 6. Okay, so we had both a positive and a negative value from this setup, and that's because we had second degree in x to begin with. But where the principal square root rule is really going to apply, you're looking at solving for x, and just quick instances here. Had the problem been given as x is equal to the square root of 36, not x squared is equal to 36, but x is equal to the square root of 36. Again, so you have an even root or square root of an expression cannot reduce to a negative constant. So, and it's kind of like if you were to enter 36 into your calculator and then push the square root feature, you have only one display, and that would be the number 6. And just like x is equal to the square root of 100, and you would have that x is equal to 10. Okay. And now I'll mention this too. I didn't do this with any of the other groups. Let's say you have like x is equal to, let's say, the 4th root of 16. Okay, now there are additive inverse numbers that if you took it times itself, times itself, times itself would give you 16. That would be positive and negative 2. But in this case, okay, we're looking at the even root of 16, and that is only going to reduce just to the positive portion. So that is going to be x is equal to 2 itself. 4th root of 16 is going to be 2. All right. Now, in looking at what we have carrying over for x, and let's say that if we have x not outside the radical but inside, and let's say if we have the square root of x plus 1 is equal to 8. Okay, so for what we have, first of all, I have the square root of x plus 1 is equal to 8. So you have an even root with the square root of x plus 1, and the square root of x plus 1 reduces to positive 8. So there's no violation of the principal square root rule in this case. And so we can proceed, and to get rid of the radical, I can undo the presence of the square root by squaring out both sides. So the square root of x plus 1 raised to the 2nd, this will go to x plus 1. And 8 squared is going to be at 64. And if we have that x plus 1 is equal to 64, remember we're going to have that x is equal to 63. And again, 63 plus 1 is 64. Square root of 64 is going to be at 8. And if we have, let's say, we have something like the cubic root of x minus 1 is equal to 4. Okay, so you have the cubic root of x minus 1. So you have an odd root in this particular case. And to undo the presence of cubic roots, I can just cube out. So in this case, the cube of the cubic root of x minus 1, so this will go to x minus 1. 4 cubed, we have 4 times 4 times 4, which will be 64. And with x minus 1 equal to 64, if I add 1 to both sides, we're going to have the x is equal to 65. And just a couple of cases here. If I have, let's say, that the square root of x plus 5 is equal to negative 2. Okay, now this one is not going to have a solution, okay, because square root of x plus 5, that's an even root. And again, the square root or any even root of an expression cannot reduce to a negative constant. Okay, so you have an even root, and this particular item, this is going to have no solution. And again, that's because of the principal square root rule. Now I'll just say, I'll just shorthand this, you have PSR or PSR rule. And let's say if I have the cubic root of x plus 5 is equal to -2. Now, in this one, I can work this out because you can have an odd root of an expression to reduce to a negative constant. Okay, so in this one, okay, so you have PSR rule does not apply to odd numbered radicals. Okay, so odd root radicals are not restricted by the principal square root, just as the square root or fourth root radicals or any other even root radicals would be. So we can continue. So the cubic root of x plus 5. We can take care of the radical by cubing. And so we have x plus 5 is freed up, and -2 to the third. You have -2 times itself, and that's going to be at -8. And so we have for the solution in x, if we take 5 away from both sides, we're going to have that x is equal to -13. Okay. All right. Tell you what, just for the next few moments, let's say we find the solutions, if any, of x. Or find the solution, if any, to x. Okay. And we'll say just for the items here, and we'll say that we have x is equal to the square root of 400. And we'll say that we have the square root of x minus 20 is equal to 3. And we'll say that we have the cubic root of x plus 2 is equal to -3. And we'll say finally, okay, then we have the square root of x minus 12 is equal to -7. Okay, for what we have for the first item, we have that x is equal to the square root of 400. Okay, notice you don't have x raised to the second power in this one. You have just x, or x to the first power. So we're going to have one solution in this particular case. All right, so you have x is equal to the square root of 400. Now 400 is a perfect square number, and the square root of 400 is going to be positive, and the only positive number times itself that will give you 400. Okay, that is going to be 20. And we have for the next, okay, now we have the square root of x minus 20 is equal to 3. So you have an even root expression, okay, equal to a positive constant. So this setup is in compliance with the principal square root rule. So we can proceed in taking what we have in this equation and squaring both sides. So we have for the square root of x minus 20. Okay, this would be x minus 20. And we have is equal to 3 squared, which is 9. And for x minus 20 equal to 9, okay, if I add 20 to both sides, so we have that x is equal to 29. Okay, so we have like 29 minus 20 is 9. Square root of 9 is equal to 3. And for what we have with the next portions, I'm just going to mention for the square root of x minus 12 equal to negative 7, we have an even root. And again, the even root of an expression cannot reduce to a negative constant. And because of this, okay, we have no solution, again, because of the principal square root rule. And once again, we have with odd root functions, those are going to be immune from the principal square root rule. And here we have the cubic root of x plus 2 is equal to negative 3. So while even root expressions cannot reduce to a negative constant, odd root expressions, on the other hand, can. And so I can proceed and find out what the solution or the solutions to x will be. And so in cubing out, okay, we have x plus 2 is equal to the cube of negative 3. So you have negative 3 times itself times itself. So this will be negative 27 and getting x by itself. So if I take 2 away from both sides, and so we have for the solution in x, okay, that is going to be equal to negative 29. Okay. So for these cases, we've had the variable x to appear once. Now, let's say that if we have multiple appearances of x potentially, but what I want to do here is that for some of the special cases, let's say that if you're looking at solving for x, and I'll show you one equation that has two methodologies. So you have something like 4 times the square root of x plus 1 is equal to 7. So you have 4 times the square root of x plus 1 is equal to 7. Now I can isolate the square root of x plus 1 if I divide the equation by 4. Now this is going to be optional. But here we have the square root of x plus 1 is equal to 7/4. So I have an even root radical set equal to a positive constant. Okay, and so there is going to be at least a solution, or at least one solution in x. So if I were to square both sides, so as to undo the radical, so I have the x plus 1 is equal to, again, 7/4 squared. Okay, so for the square of the ratio, 7/4 times itself, this is going to be 49 over 16 . So x is going to be 49/16 minus 1. Again, so we're looking at combining. So you have like 49 over 16 minus 1. This would be like 49 over 16 minus, like 1 over 1. And converting 1 over 1 into 16ths. So your value in x, in this case, is going to be a non-integer, which would be at 33 over 16. Now another way to do this, say if you do not want to work with fractions right away, same problem, but just a different follow-through or pathway to getting the solution. Say 4 times the square root of x plus 1 is equal to 7. Now instead of creating a fraction, what I can do, okay, so you can still have a positive term times the square root comes out to a non-negative value. So I'm at liberty, okay, to square both sides of the equation. Okay, now 4 squared is going to be 16. The square root of x plus 1 squared is going to be x plus 1. 7 squared, okay, that is going to be at 49. Okay, and let me mention something. If you square something like this, like a coefficient times a square root, and I squared that portion. Now, if you notice, we're going to have the square of the factors, but the squaring does not undo the multiplication. So we still have, once you square out, you're still going to have multiplication residue that's going to be carried out. So here we're going to have the distribution of 16 all over x plus 1. So this will translate out, in other words, I've seen some careless mistakes like 16x plus 1, but it's going to be 16 times all of x plus 1. So this will become 16x plus 16 is equal to 49. And if I take 16 away from both sides, so 16x is equal to 33. And you still come out to 33 over 16. 2 different pathways, and both are correct. And the same results. They have 33 over 16. Now let's say that if we have a situation where you have x to appear twice, and we'll say that we have that x is equal to the square root of 2x plus 3. So you're looking at determining the value or the values of x. So you say x is equal to the square root of 2x plus 3. Okay. And so what I can do is I can square both sides. And with squaring both sides, so we have the x squared is equal to 2x plus 3. So here I have a quadratic equation. If I put this in standard form, just take away the 2x and the 3. And we have upon factoring, so we have the quantity of, let's say we have x plus 1 times that of x minus 3 is equal to 0. And upon applying the zero product property, if I set each of the factors to 0, so we have apparent solutions with -1 and +3. Now, anytime you have an even root radical equation, like in the case of the square root, you want to check the results. And you don't have to write out the checking, but I just want to mention. So if I were to check x is equal to -1, so if I have x at -1, so I have that -1 is equal to the square root of 2 times -1 plus 3. And 2 times -1 is -2 plus 3. And negative 2 plus 3 is going to be 1. And guess what? Square root of 1 reduces to only 1. And we have a false statement here. And negative 1 does not equal positive 1. So this value of negative 1, it is not going to check out. So this one is going to be extraneous. Okay, so we could have had potentially up to 2 solutions. And now it looks like there might be 1 solution or no solution. And if I check x equal to 3, okay, so I have just going back to the same equation, but this time with the input value of x at 3. So I have 3 is equal to the square root of 2 times 3 plus 3. Again, you don't have to write all this out, but I just want to kind of do a bit of an expository display of what you're encountering. So you have 2 times 3 is 6, and we have plus 3, and we have 3 is equal to the square root of 9, and again, square root of 9 is going to be at 3, so this is going to be true. So while negative 1 does not check out, 3 on the other hand does. So for this equation, there's going to be 1 solution, and that is going to be with the number 3. And let me give you just one more case here. If I have something like if I have something like 5 times the square root of 2x minus 3 is equal to 9. Okay, now I'm looking at solving for x. Okay, so I have 5 times the square root of an expression equal to a positive constant. Now you can isolate the radical and set square root of 2x minus 3 equal to 9/5. But I think what I'm going to do here is just go ahead and square both sides. So you got 5 squared is 25. Square root of 2x minus 3 squared, that is going to be 2x minus 3. And 9 squared comes out to 81. Alright, so I have squared out all the factors and the numbers involved. Okay, but I still had the distribution of the square of 5 to carry out over the square root of 2x minus 3, so we have 50x. And we have 25 times negative 3, so this would be a minus 75. We have is equal to 81. And so looking at what we have now, so we have 50x. And we have is equal to 81 plus 75, so this will be 156. And we have with division by 50. And we have that x equal to 156 over 50. And since we have a ratio of even numbers, okay, that can be reduced all the way down to, let's see, 78 over 25. All right, and once again, your Alex first homework, okay, is due this evening, and now just some items to go ahead and be looking into. And we say we have regarding the lead into working with radical equations. Tell you what, on page 70, just be looking into numbers 103 to 108. And also number 110.